All right, welcome to Introduction to Quantum Field Theory, episode 31. This will be a relatively short video just introducing the Dirac equation's Green's function. So we're going to start with the Dirac-Lagrangian, which has an interaction potential, which means that we have the Lagrangian here, which is the conjugate spinor times I gamma mu partial mu minus mc, and plus some interaction potential, which will depend on both of these fields. All right. And then we'll use the Euler-Lagrange equation to figure out what the inhomogeneous Dirac equation looks like. So recall that the Euler-Lagrange equation is the partial derivative of the Lagrangian with respect to the conjugate spinor, and then the gradient of the partial derivative of the Lagrangian with respect to the gradient of the conjugate spinor. So we have this, or so we can say instead of implying there, of implying here. So therefore, this implies if we do the left-hand side first, we take the gradient with the derivative with respect to the conjugate spinor. Then this side will disappear and we'll be left with this. So on the left-hand side, we have I gamma mu partial mu minus m, then c. And here, now we're doing the right side, so the derivative with respect to the gradient. There are no terms here or here that depend on the gradient of c. So the right-hand side will be 0. Oh, and then I forgot on the left hand. Continuing on the left-hand side, so still doing this. You also have this, the derivative with respect to the conjugate spinor of this. So plus the derivative with respect to the conjugate spinor of the interaction potential. And this further implies that the inhomogeneous Dirac equation is this. So it looks remarkably similar to the form we had for the inhomogeneous Klein-Gordon equation. So I believe yeah, except here there's no minus sign. There's no minus sign here, but there's a minus sign here. Okay, so recall that Dirac spinors have 4 components, so that they're basically column vectors like this. So technically, it's best to rewrite. So technically, the reason I'm pointing this out is because it's going to be important for the special solution. So technically, you have that these have components. So this is one component, and then this is one component, one component. So as we did with the scalar general solutions, we'll have a spinor general solution, which will look like this with, of course, components alpha. And the general solution will be in space. depend on space, be the integral over y of alpha beta, and we'll discuss what this means in a sec, why there are two. And then the derivative of the interaction, and now the interaction here relies on these fields, which rely on the position y. And this will be some component beta. So a general solution will look like this. It's not super in line, so just trying to get it look a little better. There we go. So a general solution, the component A, will be, or alpha will come from some component of this of the derivative of the interaction potential. So we'll just call this the interaction. So some component of the interaction interacting with this special solution will return this general solution. And because this is a component and there are four components here, this is like having 1, 2, 3, 4. And then you have something that's over here equal to 1, 2, 3, 4, which means that the thing you're going to have in between. Okay, well, I messed up some of the numbers here, but you can see that basically you have column, matrix, column. And so this is a matrix. That's why it has two indices, because it's talking about the row and column. And this is just a column. So the special solution we want it to satisfy a delta distribution. The special solution must satisfy I gamma mu partial mu minus m. And then if we think about this, this is in a Clifford algebra, this is technically a matrix. So now we're looking at the alpha and sigma components of the matrix times the special solution times the sigma beta component of the matrix, and minus partial x mu minus y mu. And then this tells us, this right here is the basically the identity matrix. It can be, you can think of it as the Kronecker delta, such that if alpha and beta are not equal, then this will be 0. But as we're basically summing over all the indices of matrix, this is the identity matrix. And again, we're going to be given the solution, or we'll assume. So again, we will assume we are given the solution, because the mathematics of actually solving for this are beyond us. So the special solution matrix is going to be the integral over the wave vector space e to the minus I k mu x mu e to the plus I k mu y mu. And then I have this right here, minus k sigma, or no, let's choose a different one from sigma. We'll do lambda. Okay, lambda plus m squared, then minus k rho gamma rho plus m alpha beta. So this looks hideous, and you would be right to think so. It is hideous. I'm glad that this is not going to be my main area of physics. And basically, it's saying that the special solution, the A alpha and beta uh, component, or so the element of the matrix, will be determined by summing over this and seeing the kind of the interference between these two positions interacting the between position y and position x in the exponential, and then you have this, which I called before. That this is the definition of the Dirac delta, the delta distribution. So that's what this is, and this right here is this is a normalization factor. This is a normalization factor. And now we can use this to solve the inhomogeneous equation and finally interpret some of the other terms that we have in the perturbation solution from the last video.